Okay, so this lesson serves as our introduction to our whole series unit. And I think it gives a pretty good overview of what's to come. So Taylor polynomials, we're going to be using them, if you take a look at objective 1, to approximate a function. So general idea here is that we've got something like a transcendental function. We have e to the x, cosine x. Those things aren't as easy to deal with as polynomials. So the idea is to take that transcendental function and approximate it with something that is way easier to work with, some kind of polynomial. All right. Second objective, if we make some sort of approximation using one of these polynomials, we kind of want to know how far off we are. What's the error? And so that's what the second objective is about, calculating the error of a Taylor polynomial using what's called the Lagrange remainder. Okay, both of these things absolutely on the AP exam. If you take a look at your assignment, for the first objective, you're not using your Stewart textbook. Instead, you're going to use some pages from the Larson plus a homework supplement, kind of refine some of the things that were in the book, and then give you some AP practice. All right, so let's take a look at a warm-up exercise. Evaluate each of the following. So we've got 3, that's pronounced 3 factorial. I know it's tempting to shout it or to say it with some kind of enthusiasm. 3 in, but it's just 3 factorial. Okay, so what that means, factorial just means that you're taking that number and you're multiplying it by all the integers that come before it, all the way to 1. So, for example, 3 factorial is the same thing as 3 times 2 times 1, which is 6 times 1, which is just 6. Okay, and we will definitely recognize that quite a bit in this lesson and some future lessons. Okay, in factorial, well, there's not going to be much for us to simplify. It's just understanding how this thing would expand out. It would be n, and the integer that's right before n would be n minus 1, and the one right before that would be n minus 2, and then you would keep going, times dot dot dot, times 2 times 1, and so on. Okay, now the main point in number 3 is that this division problem, stuff like this happens pretty frequently with factorials, and it's actually a pretty easy simplification. And the reason why is because I'm going to take n plus 1 as a factorial and rewrite it as n plus 1, and then the number that's right before n plus 1 would be n, and then I'm just going to turn that into n factorial, right? If I multiply n plus 1 times n factorial, I'm going to get the original n plus 1 factorial. I did that so that I notice that the n factorial on the bottom and the n factorial on the top will now cancel out, leaving me with just n plus 1. Pretty handy technique. Okay, let's look at the next warm-up. There's quite a few here. Okay. So find the equation of the line tangent to the graph, f of x is equal to e to the x at x equals 0. Also a very common question type on the AP exam. If I'm going to write the equation of a tangent line, I need 2 pieces of information. I need a point, and I'm going to get that from just sticking 0 into the function like so. So here's e to the x, and I stick 0 into the function. Of course, I get 1. I plot the point. All right, I've got a point. The second piece of information that I need, of course, is the slope. Where am I going to get the slope? I'm going to get the slope from the derivative, right? The derivative gives me the slope at every single point on our graph. So I take the derivative of e to the x is still e to the x. And then we plug 0 in again, the same exact point. We still get 1, so we have a point of tangency, 0, 1, and then we have a slope of 1. So we're going to put both of these pieces of information together into our friend, the point slope form, thusly. And then usually, I mean, you could leave it like that, save, stop, whatever. But I'm going to go ahead and simplify, bring that 1 over. I know this is a very strange way to write this one, 1 plus x instead of x plus 1. How unconventional. You'll see why shortly. All right, and then of course, I'm going to go ahead and graph that one. All right, so there we go. We found the equation of the line tangent to the graph f of x at x equals 0. One of the reasons why I do that is because a tangent line is often used to approximate that function really, really close to the point of tangency. So Of course, if I'm looking at the graph here, ooh, cool. Where's the laser pointer here? Oh, there it is. Instead of these red marks. If I look at the graph right here, really, really close to the point of tangency, I can see that the graph is pretty close to it, right? But as soon as I get further and further away, it's getting less and less accurate. Okay. Number 2, use your tangent line to approximate f of 0.5. This is what I was saying, that we use this tangent line to approximate function values that are pretty close to that point of tangency. And so if we're finding f of 0.5, that's e to the 0.5, which is essentially the square root of e, like that is not something that you'd be able to get without a calculator. But the tangent line, if I just plug in 0.5, 1 plus 0.5, I get 1.5, it's saying that, the square root e is pretty close to 1.5, right? And that was so much easier to work with than the transcendental function e to the x. The next question, so whenever we get an approximation, it's always nice to know, did we just over-approximate it? Was it too big, or did we under-approximate it? Is it too small? Well, the picture here gives us a visual clue of what just happened. We obviously under-approximated it because our tangent line is underneath our function. However, in most cases, you're not going to know where that tangent line is relative to the function unless you do a little bit of calculus. And what is the calculus that you need to do? You need to look at the second derivative, because second derivative tells you something about the concavity, and the concavity tells you where the tangent lines are going to be. So here's the original function, here's its derivative, here's its second derivative, and then notice, of course, for e to the x, it's always e to the x, no matter how many times you take the derivative, but e to the x as a function and function values on it are always positive. So no matter what, the second derivative is always positive, which means that your original function, no matter what, is concave up. If your function is concave up, then the tangent line has to appear below your function, and it's going to under-approximate the value of your function at any particular value. So let me just kind of recap that just a little bit, because we only looked at one side of that. All right? So right here we have a function which was concave up, and I knew that because the second derivative is greater than 0. Concave up. And we have just under-approximated, under-approximated the value of our function. If, however, our second derivative was less than 0, that means that our shape would be concave down. And if I sketch a little graph of this, whoops, that is not concave down. Here's concave down. Let's put a tangent line up there. No matter what, whenever I go to draw the tangent line on a shape that's concave down, it's going to be above the graph, so we are over-approximating our function, right? Very handy thing to know whenever we're doing some sort of approximation, which brings us to the fourth part of this second warm-up question, like it hasn't lasted long enough already. What is the error in your approximation? Well, error just means that you take the difference between the actual value and the approximation. So this kind of assumes that we must have known the exact value anyway, and we're just going to pull that from the calculator and approximate it to 3 decimal places, 1.649. And then here's a graph of that and a point on it. All right, and then our tangent line approximation, if you recall, is just 1.5, and then here's a graph of that. So the error is just the difference between those two things. I subtracted, it's pretty small, right? It's 0.149, and here's that on the graph. It's just this tiny little segment that's right there. Now that tiny little segment is going to grow larger and larger the further we are from our point of tangency right here, right? This is going to get bigger and bigger and bigger. So one of the things that Taylor polynomials are going to do for us is kind of widen that gap. It's going to get our graph closer and closer to our approximation, or I should say that in the other direction. It's going to take the approximating polynomial and get it closer and closer to our function over a much, much larger interval, right? Which brings us to the main objective for this first part, which is about approximating a function with a Taylor polynomial. And guess what? We just did that. Because a tangent line is an example of a Taylor polynomial, it just has degree 1. So for the rest of the lesson, we're going to increase that degree. We're going to make it a Taylor quadratic, then a cubic, then a quartic, and get closer and closer to our function and have a better and better approximation. And that's basically the main idea behind Taylor polynomials.